Our next section is going to be quantum numbers. And what we can say about quantum numbers is that electrons are identified by a set of 4 quantum numbers. These quantum numbers reveal different aspects of each electron. And there's something called Pauli's exclusion principle. And what this tells us is that no 2 electrons can have the same 4 quantum numbers. So we know that the electrons make up a lot of the properties of each atom and each ion. And each of these electrons and how many electrons and how they interact with each other is going to give us a lot of information about all our properties of matter. So what we can say is that no 2 electrons can have the same set of 4 quantum numbers. So these quantum numbers are going to help us identify and keep track of each of these electrons in a particular atom. So let's go over what these 4 quantum numbers are. Quantum number 1 is referred to as the principal quantum number. And it's abbreviated by the lowercase letter n. And n represents the distance from the nucleus. And these are only positive integers. And we've seen this n before in the Bohr model and also when we do the electron configurations. It's going to indicate the energy level the electron is in. So if we have a quantum number n equals 1, that refers to the 1s orbital. If we have a 2s or a 2p orbital, n is going to equal 2. For the 3s, the 3p, and the 3d, the principal quantum number is the 3. So we've seen all these before with the electron configurations and the orbital block diagrams, and what that principal quantum number tells us is it tells us how far away from the nucleus or which subshell we're located in. The second quantum number is the azimuthal quantum number, and it's abbreviated by the lowercase letter l. This is the orbital quantum number. And this indicates the type of orbital in which the electron is moving. And the azimuthal quantum number L can equal 0, 1, 2, or 3. And if we're in an s orbital, the azimuthal quantum number is 0. If we're in a p orbital, it's 1. A d orbital, it's 2. And an f orbital, it's 3. The third quantum number is the magnetic quantum number, and it's abbreviated m sub l. So a lowercase m with an L subscript. And this indicates the 3-dimensional orientation of the electron. So m sub L can have values from minus L to 0 to positive L. So these are the numbers or the values that m sub L can take on. So for example, if our L value is 0, 1, 2, and 3, the m sub L values that are possible for an electron in the s orbital, the m sub L value is always going to be 0. If we're in a p orbital with an L value of 1, we can have -1, 0, or +1 for the values of m sub L. If we're in a d orbital, we have to have 5 numbers to indicate what that is. So the L value is 2, m sub L can range from -2 to +2. If we're in an f orbital, the m sub L values range from -3 to +3. And note that the m sub L values are also integer values. So this can be represented if we look at the orbital block diagrams. For an s orbital, there's only one block. So it's going to have one value for m sub L, which is 0. For a p orbital, there's 3 blocks, so we have to have 3 different m sub L values for this quantum number. There's going to be 0, and by convention we put the +1 over on the left-hand side and the -1 over here on the right. The d orbital, there's 5 blocks. So in the d orbital, we have to have 5 different m sub L quantum numbers to show which d block we're in. So we start with +2, +1, 0, -1, and -2. For the f orbital, we have to have 7 values. So we put a 0 in the middle, then it goes +3, +2, +1, -1, -2, and -3. So these are our 7 values for the 7 blocks of the f orbital. We'll get into more examples later of specific elements or atoms, and this should make a little bit more sense. The last quantum number is called the spin quantum number, and the spin quantum number is abbreviated with a lowercase m sub s. And there are 2 different values. There's +1/2 for spin up, and there's -1/2 for spin down. So by using this set of quantum numbers, we can set up a system where we only have one set of 4 quantum numbers for each electron in a particular atom. And in the next video, we'll go over some examples of how that's done for specific atoms.